Once again, good afternoon.
Good afternoon.
And once again, I welcome you all. And then we try to do some interesting things. Okay? Good. So, beta, alpha, under a unity transformation goes as beta, together u, alpha, beta, alpha, under a unity transformation goes beta, together x, u, alpha. This I would write as either or so we are considering the transformation of our, let us say, the inner products defined either by, it is also an inner product of beta and alpha. This is yet another new state vector and its inner product is beta. Okay? And how do these inner products transform under the so-called unitary transformations? For the unitary transformations, we have u dagger u equal to a unit operator. Okay? Where you define an unitary operator by definition is the thank you. So, right now, we consider a special case of unitary transformations, namely the time evolution operator. This is also an unitary transformation, okay? And the time evolution operator is also satisfies u dagger u equal to unit operator. Okay? Yes? Okay. So now there are two different scenarios in front of us. I could consider this as a product of this, and in between sandwich is my operator x. So what happens here? This u is my time evolution operator. This would evolve this state in time. Okay? And so here the state vectors evolve in time. And state vectors evolve in time, then state bras also evolve in time. However, the operator x remains fixed or frozen in time for all time the same. In this scenario, the state vectors and the state bras, they remain fixed or frozen with time for all time, whereas the operator evolves with time. Okay? Alright? So that is the main idea, and this first approach is called as your in the Schrodinger representation, your alpha goes to u alpha, and in the Heisenberg representation, your operator x goes to U dagger. Okay. The first one, the operators remain frozen in time or fixed in time. The second approach, the state vectors and the state bars, they remain fixed or frozen in time, and the operators evolve. Okay. We have derived the corresponding equations of motion. We have derived the Schrodinger equations. We have derived the Heisenberg equation of motion. So now we are ready to determine or to discuss or to study the dynamics of any given quantum mechanical system. Okay, very good. The very first thing, so supposing I set T0 equal to 0, then I could write my operator U as U of T. This is e to the power or exponential of minus iota y s cross t. So I have just simply set T0 equal to 0 for simplicity. Okay, so the initial time is 0, very good, and the Heisenberg operator is my, this is a function of time, so this is equal to E dagger T and A of S and of T. Okay, so this is operator in Schrodinger representation, and therefore it remains fixed in time. And this is my U dagger. So the time evolution of this operator in the Heisenberg representation is determined by this whole object U dagger AS into E. Alright, very good. So here the A, what would be this? This would be, so essentially this gives me the initial condition. So if you determine this object at time t equal to 0, how should it be? This would be identically the same as the Schrodinger, which does not evolve with time. It also means that it is the Heisenberg operator but at the initial time. Okay. So this is a different, it's just a matter of looking at the things. And also now alpha T0 and T, this is my Schrodinger state vector, and this is equal to your T0 here is equal to 0. So this is U of T alpha T0, where T0 is equal to 0 if I like T0 is equal to 0. Okay, and what is my Heisenberg state vector? Alpha T0 equal to 0 and T. Okay, and this is my Heisenberg operator, Heisenberg state vector, and this has to remain fixed or frozen in time, so it must not evolve, and therefore this is equal to the same at the initial value. Or if you like, no, this is the best thing, okay? So, this guy, the Heisenberg state vector, or the state vector in the Heisenberg representation, it remains the same as it was at time t, 0, for all times. Okay, now let me try to see if I have S alpha T0 equal to 0 and T and AS, then alpha T0 equal to 0 and T. What is this object? This object is the expectation value of this operator in this Schrodinger representation. Okay, this is the expectation value of this operator in the Schrodinger representation. And what do? Now this is equal to u times alpha. So if you like, I can write u of t. Okay, so this guy is u of t times this state vector. So this operator would evolve this state to this state at time equal to t. Alright? Similarly, this would be alpha d0 equal to 0 and of t. Is this alright? Okay? Very good. And therefore, I could write down this object as equal to alpha so please read these equations very carefully. I repeat from here. This is my Heisenberg state vector or a state vector in the Heisenberg representation. Alright? And of course, this is my state vector in Schrodinger representation. So here, this u of t, the time evolution operator, evolves this state which was defined at the initial time t0 equal to 0 to a later point of time at t equal to t. Is this alright? Okay. So now I want to consider the expectation value of this guy in the Schrodinger representation. And I have to take the operator and the state vector and its condition adverse. That is how you determine the expectation value of an operator. Very good. And then I know here I am just using this equation. This is u of t. This is u of t. So when this operates on this, it evolves to this state. And here I am using Hermitian adjoint of this equation. So Hermitian adjoint of this equation would give me the time evolution of the state graph corresponding state graph, which is this one. Okay? And this, you see, now you have to identify that this object and this object, they are the same object. Why? Because if I want to write down the expectation value in the Heisenberg representation, then this guy remains fixed or frozen for all time. So it is the same object which is here. Alright? And the same thing applies. Okay? And this is my operator in the Heisenberg representation. And therefore, what do I infer? That the expectation values in both the representations are identically the same. They do not change. So I can say that the expectation value of an operator remains invariant with respect to different representations. In a short while, I would introduce one more representation, which is called as Dirac representation or intermediate representation or interaction representation. And you will find that the expectation value of an operator would again remain the same. So it would remain invariant. Alright? In all the representations. Is this okay? So, okay, let me now remove some of the stuff from here. So, if you like, I think I will remove this. Let me leave this last piece here as it is. So, let me leave this here. Now, let me consider. So, you see, expectation value of an operator remains invariant under both the representations. Alright? So, it is a very crucial definite thing. Okay? Expectation value. And now, one more object that is also equally separate is the commutation relation of the operator. So, you consider a commutation relation of two operators in any representation, whether Schrodinger or Heisenberg. It would remain the same also in the other representation. Okay? Let us try to see. So, supposing A of S and A of S and B of S is equal to, so this is the commutation relation of, we are assuming that let this be the commutation relation obeyed by any two operators A and B. So obviously A and B are Hermitian, C is also Hermitian, commutator left hand side is anti-Hermitian, and so it's also true for the right hand side is also anti-Hermitian. Okay? Alright? Now we want to see what happens to the operator, to the commutation relation in the Heisenberg representation. Alright? Let us see this. So you consider A of H equals to U dagger of A of S, U of A, you consider B of H, this is also equal to U dagger of P, B of S, and U of P. For U of P, I know this is given by exponential of minus IST by S cross, and therefore U dagger also I know is exponential of plus iota by S cross into S into T. The same thing also holds here and here. Now, let me write down the commutation relation of these two operators, and what do I get? This is obviously A of S, B of S minus B of S. Okay. Alright, and this you can put now these values for AS, BX here, BX and AS. Okay. Simply put these values, and then I can very easily take e to the power or exponential of this is common, and ax here, and this is ax, so this is ax, and let me write e to the power minus I and t by n cross, and then ds is, then bx is again e to the power of I plus b by x cross into, this is 1, and now b of s and e to the power of minus I x cross. Okay. And minus, this is a of x, b of x minus these two terms. Okay? Alright? And here, now you will see that this guy goes to 1, unit operator. This is u dagger. U dagger is 1. Okay? Similarly here, in between, in the center, u dagger would be 1, and therefore what I would get is e to the power or exponential of ds cross and a of s, b of s minus b of s, a of s into exponential of Can you check this? Yes? Very good. So, and now for this I would like to substitute here equals to I ds. So what do I get? Here I get and this is nothing but I dx. Is this clear? This is u dagger. This is u dagger I dx and u. So this is I dx. Is this alright? So you see the whole quantity a of x, b of x, the commutator gives me back I to c of x. Okay. So this is my operator. Heisenberg representation. These two I started initially as the operators defined in the Heisenberg representation. Okay? So they are defined in the Heisenberg representation, and here all the three were defined in the so-called Schrodinger representation. So they obey the same property. Alright? Okay. I want to now, I need some space, so let me remove. Can I remove this thing on this side? Although I would need this for, and I would also need this. So what do I do? Okay. Alright. I have only two options, either to erase this one or that one. Okay. So I prefer to erase this one. Let me create this here. This is of all right. Okay. Right. Okay. Good. Now let me introduce one more representation called as the Dirac representation. This is also called as IR. IR can stand for two things: interaction representation as well as intermediate representation. Here, I is this intermediate representation and I is this interaction representation. Okay? So I must explain to you in words. Here, in our two approaches that we have considered so far, in the Schrodinger approach, Schrodinger representation, the time dependence is carried completely by the state vectors and state branch of the theory. And operators do not carry any time dependence. They remain the same, fixed for all times. They remain frozen in time. They remain the same for all times. In the second representation, Heisenberg representation, other way around. The operators evolve in time and the state vectors and the state branch remain frozen, fixed in time. Alright? Now, I want to talk about yet another representation here. Part of the time dependence is carried by the state vectors and part of the time dependence is carried by the operators. So obviously you would call it an intermediate representation because part of the time dependence is carried by state vectors, state branch, and part of it is carried by the operators. Now, how do we call it interaction representation? I have to write down something before I could justify it. Okay? So what do I do? I consider theories which here I write as equal to S0 plus S prime, and S prime is a function of time. So, actually, these are physically more interesting theories. These are interesting theories. These are interesting theories. Okay? This is called as the free part of the Hamiltonian and this part is called as the interaction part of the Hamiltonian. This part, the Hamiltonian, does not depend on time. This part depends on time. Okay? Alright? So in all interacting theories, you will always have some S prime which is in addition to S0. Alright? Okay? Is that okay? On the website, very honestly speaking, I have been teaching physics here for many years now, and this particular year, I do not get the facial expressions from the students that I used to get. The facial expressions tell me that you are understanding the things that I am teaching. And your facial expressions really do not reflect that. I'm sorry about my remark. But maybe you are not devoting time at home, or I do not know. It doesn't apply to everybody, but it applies somehow. So, not only with respect to this subject or with respect to me, in general, the only key to good success for this master's course is that you have to study things simultaneously at home. Almost every day you have to brush up your things, come back with energy, and that gets reflected on your faces. Okay? Anyway, we have to So we have to proceed further. Here, now, let me use the superscript I, P. I define it to be exponential of iota f0 p by s cross times a of s and exponential of minus iota by s cross and t. And I also define alpha T0, let it be T0 equal to 0 and T, and I put a subscript I, which means the state vector defined in the intermediate representation. So here, this object is defined as exponential of this thing times the vector alpha T0 equals to T, T0 equals to 0 and T and X. Okay. So these are the two definitions that we introduce. So this is how an operator is defined in the intermediate representation. You would equally write it as